couple of times, not a few. All right, now recording. So, Mia, do you want to describe your full conditional distributions again? No,
Yeah,
I'm just
let's
kidding.
go.
No. If you have any, if you want me to recall that at any point, send me an email and we can go over it again. All right, so we're talking about the scale function. And I want to show what the function of scale is. When we have, so I use time.s instead of time. What scale function in R, it looks like this. And in math, it is the time minus the mean of time divided by the standard deviation of time. So we center it, we subtract off the mean, so we get it all the values centered around 0. And then we shrink the scale of it by dividing all those values by the standard deviation. And this works when you have larger values. If you have really small values with very small standard deviation, it can actually backfire, because when this standard deviation gets small, this whole equation gets very big. But for time, we're between 0 and 24, so it'll work for us. So to get back to our original units, we can take our time.s and just try and solve for time by itself. And to do that, we multiply both sides by standard deviation of time, and then add the mean of time to both sides. And that's going to equal our original time. So I have that in R. Here, we take our scaled time, we multiply it by the standard deviation of our original time, and then add the mean to it. And this is our, if we try and recover our original time, then we can just look at the time we simulated right away and then compare that to when we try and recover it and see if they're the same, and they are. So we can get back to our original time from our scaled time. Okay. Now we have three different visits. So we're going to make 3 different design matrices for each visit. So this refers to our, this 2 refers to our second visit, not observer 2, but our second visit, all the observers who visited each site on the second j equals 2. And then this is for j equals 3. So now we have our 3 design matrices for detection probability. All right, so we have our intercept and then our indicator variables for who is actually observing at that site, and then the scaled time of day that the observation took place. And these are the same for each visit. But if we wanted to allow flexibility to have different time at each of our 3 visits, instead of saying we visit the site at each visit, we can just do something like time 1, time 2, and time 3. Gives us the flexibility. And then when we make each of our design matrices, we just put this in here. Time 1.s. there, and that permits us to have different times for each of our three visits. All right, so now that's our detection, simulating our detection data. We actually haven't simulated our data yet. We're just developing the covariates. So we're developing the stuff that we would actually collect in the field. And that is who surveyed which site and when. But now we think that there are some other covariates, and I just picked a couple that I gleaned from the internet on what affects pica occupancy or habitat selection. And that is the amount of rocky talus that's out there. And Mia, you can correct me if I'm wrong here, if any of these seem funny. In that pica prefer habitat that has rocky talus, and that maybe we're only going to survey sites that have at least 50% of the area of the survey site that have 50% rocky talus. We can scale this again. And then the other one is distance to meadows. And that what I learned from a quick Google search is that pica prefer meadowy areas. Is that correct?
Yeah, it's where the good vegetation is. Yeah.
Okay, cool.
You're nailing it. You got all the pica ecology down.
All right, good. All right, so distance to meadows, and that maybe the closer they are to meadows, the more likely they are to be there. Okay, the other one I want to throw in there too is ravens. Maybe ravens affect pica because they can eat them or something, but ravens are growing in population. I've been thinking about them a lot lately. And they definitely affect sage grouse and desert tortoise. So maybe they affect pica. Maybe we don't know, and we just think this is somewhat exploratory, and we want to look at the relationship between the number of ravens out there and if it actually is affecting pica occupancy. So we also collect data on how many ravens are out there. We have count data, so we can simulate this from a Poisson with an expected value of about 5. And then we have our covariant, our design matrix X for our occupancy probability. So now with occupancy probability, remember that if we're assuming the population's closed, so we're not going to have a different X for each visit. They're either going to be there or not there. And it's not going to change from one visit to the next. So we only have one design matrix for X. We don't have 3 like we did for each potential observation in our repeat visits for our ability to detect them. So we have an intercept and then a measure of talus that's scaled. Distance to meadow is scaled, and then the relative number of ravens to each site. Okay, everybody with me on this? Let's pause here. We could maybe take a break, or not a break, but any questions?
I guess, sorry if this is kind of a silly question, but just like getting back to the overall process model for this, like what, I'm just thinking about how X is integrating and how that's different from what we've seen. Like, are we using the same X when we're estimating both the aspects of the Bernoulli distribution around like our main process model? I'm so sorry, I'm terrible at Greek symbols, but phi and the other kind of trident looking symbol that we agreed.
The trident one's psi.
Psi, yeah.
Let's see, are we incorporating, let's write out the model again, just as a review. This will maybe help.
Yeah, I feel like this is confusing for me in this like step, so thank you.
Yeah. All right, so we have our data, which we're about to simulate. Y are zeros and ones for each site I, and then for each observation, each time. We're calling those J here. And this is if we were in Excel, this would be Y for site 1, our first visit 1, Y for site 1, our second visit, and Y for site 1, our third visit. And then we have Y for site 2 and our first visit, Y for site 2 and our second visit, and Y for site 2 and our third visit, and so on for however many sites we have. So this is on the top, we have J equals 1, J equals 2, J equals 3, and then I equals 1, I equals 2, I equals N. And we're saying that each one of these, whether it's a 0 or 1, is going to come from a mixture of two distributions. When the animal's truly there at the site, then one of our Bernoullis, we have two Bernoullis here, so that's important to keep in mind. Bernoulli. If it's truly there, we don't know if it's truly there, but if it is, this is what we're going to estimate this too. But if it is truly there, then we're going to see it with a detection probability for that site in that time period. Now P, this is when we developed our W's. So we have, let me go back. Did we use P before? Yeah, we did use P, okay. So same notation. P is our probability of detection. And maybe P is constant for every site and every person. That's like our null hypothesis, that there's only one value of P and it's the same detection probability for everybody every time they go out there. But we also know that maybe it's not. Maybe there are some covariates we want to incorporate in P. So to do that, we can do what we saw before with logistic regression and say P has to be between 0 and 1, so we're going to use a link function. The most popular one is the logit link function, although there is a nice trick that if we use the probit distribution, it allows us to do something different. And if you remind me, I'll come back to that, although I won't go into the specific details. Well, I'll just, instead of forgetting about it later, I'll just say it briefly now. If we use the probit instead of the logit, it turns out all of this is conjugate. And it's a trick that was written in a paper, I don't remember what journal, but it was Albert and Chib. So Albert, then Chib. Albert and Chib wrote out this trick in that they figured out, well, we've always been using this logit function, but if we use the probit, it turns out everything's conjugate and we don't have to use Metropolis Hastings. So that's one good reason for using the probit. But anyway, logit's the most popular one. Let's stick with that. It won't be conjugate, but we can use Metropolis Hastings. And we say this equals beta 0 plus beta 1 times, let's say, time of day, plus beta 2 times observer 2, plus beta 3 times observer 3. Logit of P I. And we need T. Okay, so, I'm going to use betas. I'm going to take that back slightly. I'm going to use betas for our occupancy, not for detection probability. So I'm going to change these to alphas. Okay. Now, if the animal's not there, if the population isn't there, then Y has to be 0. We can't observe it if it's there. We're missing, this is just our ability to detect. So this is all of this stuff is our data model. Now we're interested in our process model. What's actually driving whether the animal's there or not? All right. So Z is a 0 or a 1 if it's truly or not there. So with 0, 1 data, we must have a Bernoulli distribution with some probability of success, psi I. And maybe there's just one, occupancy probability, regardless of what the habitat looks like, but we know that's probably not true. So we want psi to be able to change with features of the habitat that we think are important, or at least we want to investigate if those features are affecting occupancy probability. So psi is our occupancy probability. The probability of success, meaning the probability that the species is actually at site I. And P is our detection probability. We can do the same thing we did with P as we did with psi. And say the logit of psi equals beta 0 plus beta 1 times talus plus beta 2 times meadow distance plus beta 3 times ravens. So I wrote the W's out explicitly here, and the X's out explicitly here. But these are what's going into the W's. And they're going to be different for each of our visits. So we have W1, then for our second visit, we have W2, and then our third visit, we have W3. And this is what's going into our X's. But we have no temporal component here. So we just have one X. Okay. So here's our X's, our X matrix, talus, meadow distance, and number of ravens. Now for simulate data, we're going to simulate some true values here. That we're going to use this just for making sure our algorithm converges. We could spend some time and get our alphas all have the right sign, either negative or positive, depending on what we expect the effect to be. But our main goal, what we're going to do, we're going to do that with the real data. What we're going to do here is just make sure we can get an algorithm that works. So we simulate true values of alpha. We have 4 of them. And then we have to simulate the true detection probability using our inverse logit function. And we're going to do it for 3 different columns because we have 3 different time periods. Let's see. One, two, three, 4 columns and 4 alphas. Oh, I missed that line. Okay. Seven. Oh, I forgot to take off season.
Hey, Perry, can I clarify something really quick?
Yeah, go ahead.
So for the model statement for priors, do you only have priors for alpha and beta then?
Yes, that's right. Yeah, so I didn't include the priors. Alpha and beta are the only ones we have priors for. And there's another point I wanted to make about that too. When in the past, when we've done normal priors for parameters like alpha and beta, to make the priors vague, if we wanted to use vague priors, we use something large for the variance, something like 10,000. Well, when you do the logit transformation, there's an unexpected result that happens when you do that. And this was something that the books that were written previous to like 10 years ago or so, they were using this practice. But they were, anyway, let's look at this. So if we, let's say we want to simulate some data for let's call it kappa. And if we want to simulate a distribution from that, that is very vague. It has a big spread, but it's centered around 0. So like our norm 0. Let's just sample 10,000 observations with mean 0 and a large standard deviation. Let's say 1,000. And we can plot that, a histogram of that. And we see we get a lot of spread here. So there's a lot of probability that that parameter could be anywhere from -3,000 to 3,000. There's at least some chance that the value could take on those. So that's a fairly vague prior, right? But when we transform this using a logit transformation to get it to the 0, 1 scale, it has an unexpected effect. So if we want something to be vague, like we have for kappa here, when we go through this transformation, the idea would be we want to have something that's vague for our parameter in the space between 0 and 1. So we would want something that's flat between 0 and 1 to say each probability of success would be equally likely. But after we do this transformation, so we'll say inverse logit, I'll just say kappa 2. And we look at the distribution of that. Turns out it's very informative. It puts all of the mass at either 0 or 1. So if we specify a vague prior for betas and alphas, that seems to be vague, and it is vague on that scale, but then it goes through this transformation. We're actually specifying very strong priors for 0 and 1, and that's going to affect our inference. So if the data suggests that the probability of success should actually be about 0.5, but then we specify a prior like this, it's going to pull it away from 0.5. The prior here is going to pull it away from 0.5 to be somewhere more closer to 0 or closer to 1. So a better prior when we're on the logit scale is instead of 1,000 or 10,000 or whatever, 1.5 tends to work pretty well. So now if we take the inverse logit of that and plot that, we get something that's much more uniform between 0 and 1. So if we're using a logit transformation and you have betas or alphas connected to that, a good prior for the variance on those betas or alphas is 1.5 or 2.25 if you square it. All right, so let's see. Let's look at our true detection probabilities. We have 243 sites, 3 visits each, and the detection probability changes at each site depending on who's observing it and what time of day it is. So we want to try and estimate what these alphas are. And with our occupancy probability, we can look at the true values used to simulate the Z's. And we have a lot of variability at each site depending on the characteristics of those sites. But again, just one column here because we're assuming occupancy is constant throughout our 3 visits. All right, now to generate our data. Our data is going to be a n by j matrix, a 243 by 3 matrix. And on each site, the number of trials for the binomial distribution is going to be whether they're truly there or not, the Z's. And then we have a detection probability unique to each site. So if they're truly there, if Z truth equals 1, then it's going to simulate a 0 or a 1 with probability equal to the truth here. But if z equals 0, then it's just going to give us a 0 back. So we can simulate this and look at our data. Okay, now we have our data. Shows our observations. Lots of places we went and there were no, we didn't see any pica. At the 111th site, we went there 3 times and we saw at least one each time. Here we only saw it on the first one. Here we didn't see it on the second visit, and so on. We can make sure our simulation worked correctly by combining our data and the truth. And there should not be any observations here when z equals 0. Z has to be 1 to observe any animals. And we see it looks like every time we see something, there was indeed an animal there. All right, here's where we have to fill in the missing part from our full conditional distributions. So I have all the information in here that we needed up until the Metropolis Hastings. We have to set priors. For alpha, we say mean equal to 0, variance equal to 1.5 squared. Same thing for beta, those are vague priors. Choose some starting values randomly. Alpha. Tuning parameters, acceptance parameters, bookkeeping. And then we start our MC loop. All right, so let's develop our Metropolis Hastings algorithm for alpha. And we're going to sample all of our alphas at the same time. And we can do that because we scaled our covariates at the beginning. All right, so what's step 1? Let's work through these.
Getting an alpha dot star.
Yeah, propose a value. Propose some values for alpha. So alpha dot star. We can use a random walk. Centered on our previous value and our tuning parameter. All right, so let's take a look at alpha star, compare that to our previous values of alpha. All right, so we have our proposal distribution. Now what?
So are we going to do like if alpha star is greater than 0, then we'll do the Metropolis Hastings check? And
We don't have to do the if statement because the support of alpha is negative infinity to infinity. So there could be some negative alpha values. So like if observer 2 wasn't as good as observer 1, we would expect alpha 2 to be negative to lower that detection probability.
oh, okay.
So the values can be negative and we want them to be able to be negative. So yeah, you're right, we need to do the Metropolis Hastings step and we don't need that, but we don't need that if statement. That's only when we have positive support, we do that. Yeah, so MH1 equals,
we need to do the likelihood of the data given Zi and alpha.
yeah, so we have likelihood of the data, our binomial. We're missing a couple things, but we can figure those out as we go through. All right, so likelihood of our data, y, given z. Let's see, z. Let me go back to our full conditionals. Yeah, so likelihood of our data given zi and alpha. We need a couple things here. The probability is going to be P dot star. We're missing that. So what do we need to do?
Do you need to do a matrix multiplication between, would it be X and alpha star?
Yep. This is going to give us, let's see, W. That gives us one of our observations.
Well, then, yeah, we need that for each one. So we could either just do like P underscore 2 dot star and then do W underscore 2 times alpha star and then do the same for 3.
Okay.
In the likelihood, we're missing the sum, right? Also.
Yep.
And it needs to be D binom.
All right, right. Now that's my mistake. Let's make it the log too. What does P represent?
Detection.
Detection.
And what do we notice about some of these values?
They're
We should have
negatives.
it to be between 0 and 1.
Yeah, right. So what are we missing?
Is that where we'd put in like an if statement to reject, or just format?
Well, let's go back to our model here.
We need the logit, right?
Yeah, we need the logit. Yeah. So we have this relationship between W and alpha. W and alpha, but it's not directly related to P. We have to do the inverse logit of that to get it between 0 and 1. Instead of writing this out, I'm just going to make a function up here. Because we're going to use this a few times. Now if we look at these values, should be on the right. Oh, what's going on? Something's not quite right. 1.3, that's not right. I must have screwed up my function. Yep, there it is. Okay, so now we have values between 0 and 1. Starting values. We need z's. We have to be careful with our starting values for z. I hinted at this a few lectures ago when we were talking about the Bryant asked whether the order mattered and how we could change things around. I said, sometimes it doesn't matter in principle as long as your starting values are good. And you have sometimes you have models where we can't have a z here that is less than our actual counts. And the reason why we can't have a z that is 0 and a y that is 1 is because when we calculate the density of the binomial distribution when y equals 1 and z equals 0, it's going to give us an error because it's impossible to have a success when you have 0 trials. So if we do d binom, 1, 0, it'll give us an error. Or there's 0 probability of that. So we need to make sure that our z's, our number of trials, are at least as big as the number of successes. So one way of creating starting values that do that is to say that z is at least as big as the highest observation. So if we look at our data, y, if we saw one at least one place, like here, then we'd want to set our z equal to 1. So we can find the max. Let's see. If this equals 1 anywhere, we want z to be 1. So one way of doing that would be say if else the sum of our y's in the rows so just look at this smaller function within this. That's going to give us the sum of all our observations. If that's greater than 0, then let's say z equals 1, otherwise let's say 0. Now if we look at our starting values for z next to our y's, we should have a starting value of z equal to 1 when we see an observation, and that'll allow us to run this function. So sometimes we have to be careful about our starting values, is the point here. It has to make sense in terms of what our data are showing us. Okay, so now we're looking at alpha. We propose alpha because alpha is deterministically linked to our detection probability P on each of our 3 visits. We have to calculate that. We can combine all 3 of these into a single matrix and then look at our y's relative to our z's with detection probability P. All right, what else do we need?
We need to add on the prior of alpha.
Right. And the hyperparameter for our prior distribution for alpha was alpha dot prior dot mean. And then the standard deviation is square root of, which should be 1.5. Okay, 1.5. All right, we have a few alphas here, so we're gonna have to sum these up too. And that's our MH1. Okay. That's the numerator in our Metropolis-Hastings ratio. We can get the denominator by deleting all the stars. And starting values for P. And when we look at MH1 and MH2, they should be pretty close. They are. And calculate our ratio. If it's close to 1, we're going to accept. If not, we retain our previous values. And we did accept ours on that. Okay.
Okay, we
Any
need
questions?
logs in the likelihood for alpha.
Nice work. It's one of those things that I commonly forget, and when things aren't converging just quite right, I always check that right away. All right, how about beta?
Start with beta star.
Yep. Proposal.
So it'll be psi dot star.
Yeah. We're gonna need psi dot star. Beta in some ways is easier because we only have the 1 dimensions of the z's. So we're not gonna have to calculate 3 different p dot stars when we change alpha. So psi dot star is
The inverse logit again?
Yeah, inverse logit of what?
Of beta dot star, or no? Oh yeah. I see.
Yeah, we have to multiply by that by our covariates. Okay, so let's take a look at that. This is our occupancy probability for each site, or our proposed occupancy probability. And now we have, let's see, image one. All right, help me out with this.
Is that going to be zi given beta instead of y based on the full conditional?
Z, let's see. Yeah, based on the full conditional, you'll have just the Zi given beta and the prior for beta. Right. So what's Zi given beta? What's that distribution?
It's a Bernoulli.
Yeah. So the probability that the site is truly occupied, Z, Bernoulli, instead of binomial, we're specifying a Bernoulli, that's what the one is. And then the probability is psi dot star. We're gonna have to sum these up. Only summing over the i's though, we don't have j's. So the probability that z equals 1, given the occupancy probability. All right. And then priors. Okay. Once we have that, the second part's easy. Just delete the stars. I don't think we have specified a starting value for psi, so we might have to go up and do that. Yep. So I'll just take this, delete the stars. Those are exactly the same. What's going on? I know what happened. Okay. All right, so they're pretty close. That's good. Then we do our if statement, or calculate the actual metropolis Hastings ratio. Okay. How does everybody feel about that? On a scale of 1 to 5. Four, that's good. Meredith says 3. Probably the most challenging part was this part, right, where we have to calculate a different p-value for each of our visits because we had to change what our covariates were on each visit because the time and the person changed for each visit. So we need a different design matrix for those visits. The bookkeeping is a little more complicated in this when we have a temporal component in our models. We have to keep track of those design matrices for each of our repeat visits. And that's what we're doing here. All right, this part's going to be new too. Z is this unknown quantity or partially known quantity. It's a latent variable. We know it sometimes. We don't know it other times. And when we don't know it, we're going to have to sample it. In Bayesian inference, we treat all unknowns as random variables. So when we know it is when our rows of y's is greater than 0. So this is when we know it. When we don't know it is when our rows of y's, when we go to a site and we never saw it there. So when at each of our sites, each visit was a 0, we don't know what the true value is. These are the z's. Everywhere here where this equals 0 are the z's we're going to have to sample. Okay. So when this says true, we're going to want to sample z. When it says false, we don't need to sample z. When it says false, we know that z equals 1. So we can say z dot star when this is greater than 0 equals 1. I need a starting value for z dot star because of the way we're filling it in. And there's a number of ways to do this. I'll do it the long way first, then I'll shorten it up. So here we're filling in the known values, but now we have to sample the unknown values. So a couple of things that are new about this application. This is the first time we're proposing a integer value. I think it is. In the past, all we've done is proposed continuous values. But now this is a 0 or a 1, so it can't be 0.5 or anything like that. It has to be a 0 or 1. So we're going to propose either a 0 or a 1 for each of our sites. And we're going to have to compare that to the probability that we didn't see any animals there on our first 3 visits. So this is what we don't know here. So we could sample from a Bernoulli distribution, because that'll give us a 0 or 1. How many do we need to sample? 191. So we had 191 sites where we observed all zeros. And that's going to be the same no matter what our MCMC iteration is. So the question is, what should we put in here for our tuning parameter? We could put in 0.5, and half the time it'll give us zeros and half the time it'll give us ones. And that would be a pretty naive way to do it. It might cause some, it might be pretty inefficient. And the reason it might be inefficient is because we know something about, we know more than just assuming there's a 0.5 occupancy probability there. So I'm gonna go to the whiteboard and talk about this parameter here. So what we're doing is sampling our Z's. When y1 equals 0, y2 equals 0, and y3 equals 0. So what we know about these Z's is we went to the site 3 times, and on each of the time we didn't observe it. For that to happen, for the probability that Z equaled 1, given y equals 0, y1 equals 0, y2 equals 0, and y3 equals 0, is something that we can work out. So what's the probability that y1 equals 0?
Is that 0.5?
Why do you say 0.5?
I don't know. Yeah.
We know, let's see, it could be 0.5. Let's go back to our 3 cases where we have, when we observe it, we know Z equals 1, but when we don't observe it, Z could be a 1 or a 0. So we're interested in this right here. Actually, we're interested in both these cases. So if we go out to a site and it truly is there, what's the probability that we don't see it? And we have a name for this already in our model.
Would this be related to the detection probability?
Right. Yeah. So if Z equals 1, then we know that it was there and we didn't see it. And that probability is 1 minus the probability of seeing it given it was there. That's if we went once. Now, if we go 3 times, it's going to be the probability that we didn't see it the first time and the probability that we didn't see it the second time and the probability that we didn't see it the third time. So for it to truly have been there, the probability that z equaled 1, either this had to happen, we went out there, we didn't see it, and we went out there and didn't see it, and we went out there and didn't see it. Or, now we're going to this case, it just wasn't there. And what's the probability that it wasn't there? It's very similar to detection probability in that we already have a name for this in our model.
Well, is that our occupancy probability?
Yeah,
So psi?
close.
Wait, it's not logit of psi? Oh, 1 minus the psi.
1 minus psi, yep. Yeah, so this equation here represents these two possibilities that we know happened. We know that we went out there 3 times and we didn't see it. So this represents the first part, the probability that it was there, given we didn't see it. And this part represents this part of this equation, just the probability that it wasn't there. So 2 things could have happened. It could have been there, and we didn't see it, or it just wasn't there. So now we're interested in we're sampling z's, right? We're trying to choose a way to sample z's. So when a z equals 1, then this had to happen. But if this happens, z equals 0. I'm missing something. Okay. So the probability that z equals 1, given we didn't see it, is only associated with this. It was there. It's the probability that it was there multiplied by the probability we didn't see it 3 times. And this is going to be some fraction. And then this is going to make up the remainder of that fraction that's less than 1. So for our success probability, we can put in a lot of information here collected from our data. And that we can do phi, or psi, times the product of our p's. Now, if our detection probability is high, this should be 1 minus p. Does this function work?
Oh, Perry, we're not on your R screen.
Oh, okay. Here we go. Thank you. Oh, no. All right, so this function will take the product of all of our p's for each side, or 1 minus our p's. And if p is large, 1 minus this product, 1 minus p, the product of that 3 times, is going to be very small. And the success probability is going to be very small. So then z's are going to be 0. So we're going to simulate a lot of zeros when our detection probability is high. Likewise, when our detection probability is low, we're going to simulate more ones. And for it, a z to be simulated as 1, it also has to be there, and the probability that it's there is psi. Okay, so this, you follow me on this? Wildlifers do this a lot with figuring out survival rates, annual survival rates. But if you haven't worked with survival functions, this is probably all new. Survival and detection functions. So the probability that z, I mean, the naive thing to say would be the probability that z equals 1 equals the occupancy probability, right? And just put psi in there. The probability that z equals 1 is the occupancy probability. But what we're doing is incorporating extra information that we have from our data here. We're incorporating the fact that we know we went to these sites 3 times and we didn't observe them. So that's going to give us more information to help us simulate z's. You follow me on that?
I'm a little lost personally.
Good.
I don't know.
Yeah. Yeah. Thanks for saying something. Okay.
Like specifically when you were saying detection's high, we simulate more zeros, and when it's low, we simulate more ones. That's where I kind of lost it.
Oh, okay. I can walk through that a little bit more. We're going to a site. Let me share here. Frozen. There we go. Okay. So we have a site here. We go and visit this site on 3 different times. So in the first, I don't even know if I need this. So we go out and we look for animals at this site. We go there 3 times and we see zeros. So we don't know what z is. It could be a 1 or it could be a 0. We know that for all of our sites, the overall occupancy probability is psi. And for all of our sites, the probability that z equals 1 equals psi. That's if we don't, let's see, that's our estimate for a new site that we have no data on. We would say the probability that it's occupied is psi. That's what we're defining as psi. But we know a little bit more about this site here. We know that in general, the probability that the site will be occupied based on information from all of our other sites is psi. But we also know that we went here 3 times and we didn't see it any of the times. So that's extra information we're incorporating. So the probability that this specific site here, the probability, let's say the site 1, Z1 equals 1, equals not only the overall occupancy probability, but also the occupancy probability plus the information that we visited 3 times. And we didn't see it. Had we not gone there, our naive estimate of occupancy would be psi. But we went there and searched, and we didn't see anything. So let's incorporate that information in helping us figure out what Z really is. So now let's say detection probability was really high. Let's say for all of our sites, about half of them are occupied in general. So half our sites are occupied. We can say psi equals 0.5. And we know that our detection probability for pike is high. If they're there, we usually see them. So something like 0.99. So if we do 1 minus 0.99, this is going to be 0.5 times 0.01 times 0.01 times 0.01. And this is a small number. So if our detection probability is high, and we go to this site 3 times and don't see it, there's a fairly good chance that there's no animals there.
That helped. Thanks for explaining that.
Yeah. Okay. And that's what we're trying to simulate here. We're trying to simulate these unknown Z's. So when our detection probability is high, then, and remember, we estimated detection probability in our previous Metropolis Hastings step. And then we're going to hold that fixed when we're simulating our Z's. So when that's high, lots of the Z's are going to be 0 for the sites that we didn't observe any animals. Well, it turns out that this Z in this model is conjugate. And this is the updated probability of success for Z. And we could go through the math, but there's a lot of indicator variables. I think they go through that math in this Bringing Bayesian Models to Life book, the Phoenix on the front, if you're interested. If you're interested in actually, I would recommend this book as a follow-up to this course. They do all the same things that we do here, except they go through a number of additional models. And I think that this class is a great segue into this book. And we use all the same notation and everything. So when we talk about continuing your learning, this will be a good resource. Okay, so it turns out that C is conjugate. And the proposal distribution that we're thinking about here, the probability of occupancy and the probability that we didn't see it 3 times, turns out to be the distribution for let's see. That's the probability of success from a binomial distribution. So we can just sample it and everything's conjugate. But if you looked at when you work out the math, this is what you get. But without thinking about why it is that way from like a field sampling perspective, it's not always clear of why that makes sense. All right, so we don't need to fill in all of these, only where the sum of the y's equals 0. So I'm just gonna make an indicator variable for that because we'll use that a lot. So this is where these are the sites we didn't see any animals. I'm just going to leave the ones where we did see animals alone at 1. All right, so Z star is going to
Hey
come from
Perry,
a
can you share your screen?
yes. So I'm creating an indicator variable of where all the y's equals 0. I'm going to call that y end. Okay, and then those are the z's I'm going to sample. So I'll do the length of that indicator. Oh no, sum of that indicator variable. And then the new probability of success for this conjugate distribution is probability of observing probability of occupancy times the probability that we didn't see it 3 times. Okay. And that's it. We don't even need Z star Metropolis Hastings ratios. Because our proposal distribution gets accepted 100% of the time because it's conjugate, and we're good. Hmm. Oh, I see. Okay. Don't need this comma. Okay, and we can save our samples. We could save the Z's for each site if we wanted to. And then we could calculate the proportion of those that were ones and zeros. And that'll tell us the probability that each site is occupied, given we visited it 3 times. Or we could just save our alphas and betas. Z's tend to take up much more space because we need a column for each site. But anyway, we could do that. All right, we have 8 minutes left. Any questions?
So do we not need the starting value for Z anymore either?
We need the starting values for Z because when we first sample our alphas, we need something here. If we don't have a starting value for Z, this won't work. But just for that first iteration.
Can you show the sample Z for another minute? I don't think I got
Yeah.
everything.
There is one more step to this. So I'm going to call this phi.hat. And I'm going to take what we did here. So we don't have to put it in this big equation. So we have a binomial distribution, specifically a Bernoulli distribution, where we're trying to use the information we know.
No, we can like hear you as barely.
Can you hear me now? Okay. My headphones died. Let's see, I can't hear you though.
Do you need one of us to talk to test it?
Okay, now I can hear you. All right, let's see, there's one more small correction I have to make here. We need to standardize this. And what we have to do is put in both probabilities
to make sure this is on the right
I'm
scale.
not seeing your screen, Perry. Sorry.
Okay. Having a day of it. Okay. Final small correction in here. We have to divide this probability, the probability that it's successful. We have to scale that by looking at both possible outcomes, the probability that it's successful and the probability that it's not successful. So we have to include the first probability that z equals 1, but then also the probability that z equals 0, which is 1 minus phi. And that gives us our new probability of success for our conjugate distribution, psi. Okay. And then we have our new z's. And that's it. Those are our 3 samplers that we have: alphas, betas, z's. The z's were new. If we didn't work out the conjugate distribution of the posterior, we didn't work it out by hand, but take my word for it, this is it. And we can see why, because it's the probability of success plus the probability that we went there 3 times and didn't see it. We could still use Metropolis Hastings for this. We could sample a 0 or 1 for every z and check that with the data using our Metropolis Hastings ratios for z star and z. And that would work. It would just be a little slower to converge. This gives us 100% acceptance rate for our occupancy model. Okay, any questions? Let's come back to this for 5 minutes on Wednesday before we look at inference. And maybe I'll draw out, I'll work out analytically the posterior distribution. We can see how it relates to these 3 things.
I guess really quickly, you just recommended against not saving the new sample, like the new z value.
If you want to save space on your system, then you could not save. I think I would save the z's, especially if you only have 243 sites, because it does tell you something about those sites. It tells you the probability that those specific sites are occupied. So a site-specific occupancy probability given you visited it 3 times. And that'll be the number of z's that were 1s divided by the total number of MCMC iterations. Okay, if there are no other questions, I will talk to you on Wednesday.
Thank you.